So this video covers the basics of mesh analysis, similar to the approach that we took for nodal analysis. We won't go through an entire solution, but rather we'll just show the approach for setting the problem up, defining a consistent sign convention. And then from there you can see the entire solution on the worked course examples. So this corresponds to example 2.4 of the written examples. So recall that in mesh analysis, similar to nodal analysis, what we seek to do is write a system of equations in terms of some parameters from which we can determine any circuit quantity that we want. And in mesh analysis, those parameters are known as the mesh currents. So before we start, just recall that a mesh, by definition, and I won't write it here, is simply a loop that doesn't have another loop within it. So if you notice in this specific circuit, if we move around the outside perimeter, that by definition is a loop. However, there are 3 additional loops contained inside, therefore by definition it is not a mesh. So using that definition by examination, you'll note 3 meshes, the large one on the left and then the 2 smaller on the right. By definition, for each mesh, you want to define 1 mesh current. And then within that mesh, you're going to enforce Kirchhoff's voltage law. So in terms of the system nature of the solution, the number of your meshes is going to equal your number of your equations. So once you've identified the meshes in the circuit, you want to draw in mesh currents. Now this is where having a consistent sign convention helps. By definition, you can define the mesh current to go in any direction you would want. You can define the direction from one mesh to another to be different, but we're going to define each as flowing in the clockwise direction. And again, you don't have to do that. That's just the convention that I use in the course solution. So once you've done that, let me give you an example of how you would enforce KVL in one of the meshes. Maybe we'll do 2. The one involving the independent source and the one involving the dependent source. So clearly mesh 1 involves the 24 volt independent source. What you want to do is pick a starting node, move around the mesh, and enforce KVL. Moving across the 24 volt source, I go from minus to plus, that's a rise, or plus 24 volts. Remember that KVL is an algebraic sum by definition. You need to be careful with the sign. I have, moving from this node to that node, I have a drop across the resistor, which I'll define that way. So that drop's magnitude will be minus 10 times whatever the current is through that resistor. Now be careful here in the sense that in terms of the mesh currents, we actually have a difference of 2 currents. With respect to the passive sign convention, notice that mesh current I1 enters through the positive and leaves through the negative, and in a similar fashion I2 goes from the negative to a positive. You may remember that the way you express that current is as a difference of the 2 currents, I1 minus I2. So in a similar fashion across the 12 ohm resistor, we'll have minus 12, I1 minus I3. We're back to where we started, so that whole thing is equal to 0. And if you simplify this, you get a linear equation in 3 variables, minus 22i1 plus 10i2 plus 12i3 equals 0. And that or I should say does not equal to 0. Moving that constant 24 to the right side, we'll get minus 24. Sorry. So of course, 1 equation, 3 unknowns. We need 2 more equations just to show you in mesh 3 how that would work. And before we do that, let me just point out that the coefficients are predictable just by examination of the circuit. Specifically, what I mean by that is in mesh J, the coefficient of mesh current I sub J is simply the opposite of the sum of all resistors in that mesh. So when we're in mesh 1, the coefficient for I1 will be the opposite of the sum of all resistors in the mesh, which are 10 plus 12 or 22. And in a similar fashion, the coefficients of the other mesh currents are positive, and they're simply equal to the value of any resistors along the branch which adjoins the 2 meshes, so 10 and 12 in this specific case. So how will we do mesh 3? I'll pick the same starting node and again move clockwise. Well, that's going to be minus 12. And you notice once you get the hang of it, you don't even have to draw in the potential drops. Minus 12, I3 minus I1. minus 4 I3 minus I2. And then we're moving across the dependent source from plus to minus. That's minus 4 I0, and that's equal to 0. In this case, we're back to where we started. Now, the reason that I did mesh 3, of course you can do mesh 2 as well, and you'll have 3 equations, but notice that in mesh 3 we actually introduced an additional unknown quantity I0. But however, just by examination, we can define I0 in terms of the mesh currents. Particularly if you look by definition, I0 will simply be I1 minus I2. Make that substitution, you get your 3x3 system, solve it any way you'd like. In the examples, I believe I use Cramer's rule. And from those 3 mesh currents, you can subsequently determine any quantity that you would want in the circuit.